again. This is the third lecture on the series on Riemann integration. As you know, the COVID vaccines are going to be distributed to the frontline workers today. I wish all of them good health, okay, and it turns out to be successful so that India is free from COVID. Thank you. Let us get started. So let's get started. So in the last lecture what we did was, and I will not repeat you, okay, if P is a partition, I will write less than or equal to, it means it's a P, Q is finer than P. Q is finer than P, or P is coarser than Q, but I will still read it as Q is finer than P. Okay, this is a notation. What does it mean? It means that nodes in P are all nodes in Q, and perhaps Q has more nodes. What did we observe? We observed that with the finer partitions there is something very interesting. L of PQ was better than, okay, L of PP. Lower sum gets increased, whereas upper sum get decreased. And we also saw what was the geometric meaning of all these things, and this is also with respect to alpha, where alpha is an increasing function. Okay, all these things we have seen. Okay, and we actually proved it when Q was obtained from P using only one node, okay, namely T was between xj minus 1 less than xj minus 1, T less than xj. Okay, with this, suppose Q, okay, is obtained from P union T1 to Tk, let us say. See, this is the way we write, remember. But then when we say Q is a partition, what do we mean? It should look like this, something like x0 less than x1, etc. So when I write T1 T2 K Tk, what it means is, okay, it's a very clumsy notation. I1 and I2, between xi1 and xi2 there is a T1, and so on. And similarly between xik minus 1 and xi, since I want T1, let us make it key, xik plus 1, my Tk lies here, etc. Okay, it's a very clumsy notation, but this is a standard way of writing. All of you, I hope you understand. For example, suppose my P was a unit partition of unit interval, let us say 0, half, and let us say 3/4 and 1. Right, when I write P, now Q is P union 1/3 and 2/3. What is the partition? Of course, you know, all of you know how to write it now. 0, 1, and I have 1/4 is there? No. Okay, therefore it's a 1/3 and less than half and less than 2/3 and less than 3/4 and 1. This is what we mean by Q. Okay, yeah, but this is a short way of writing all the, in all the textbooks. This is a very standard practice, but one should understand. Okay, good. Okay, now how do I do that? By, I can prove it by induction. Let Q1 equal to P union T1. Okay, then what I have shown? I have shown that, let us stick to only the lower sums. Yeah, Q1 P, or maybe Q1 alpha, right? Okay, this is greater than or equal to LF P alpha. You understand? And Q2 is Q1 union T2. Then what do I know? L of F Q2 alpha is greater than or equal to LF Q1 alpha, but L of Q1 alpha in turn is less than L of P alpha, and so on. Do you understand that? Therefore, by induction, what we have shown is, okay, if Q is finer than P, L F Q alpha is greater than L F, this is Q P alpha. And what's the result for upper? L U F Q alpha is less than or equal to U F P alpha. Okay, these are the things which we ended up yesterday. Okay, so just quickly recall, because we are going to use it today. Okay, now between upper sums and lower sums we made some observations yesterday, namely m into maybe this is another place where it's a standard notation may be easier. When we write del xi, it is xi minus 1, and I will write del alpha I. Can you say, guess what it is? This is the, you remember in all the sums we have something like mi into something. This is xi minus 1, or in the case of alpha it is alpha xi, therefore this is alpha xi minus alpha xi minus 1. Okay, so this is a very standard notation, but usually I do not use it, but I think since I am using still this interval, it may be easier. Therefore, what is our LFP alpha now? LFP alpha is going to be mi of f if you want, and into delta alpha I equal to 1 to n, whatever it is. Is it okay? And similarly UFP alpha I. So what you had already seen is the following thing. You have seen that LFP alpha is always less than or equal to UFP alpha. That in turn is less than or equal to capital M into del of alpha. How will I write it? So I can write it, therefore it's alpha B minus alpha A, and this is greater than or equal to little m of alpha B minus alpha A. This we had already seen. Okay, yeah, so upper sums and lower sums relative to the same partition, we have this inequality. Lower sum is less than or equal to upper sum, and what we have is this chain of inequality. Now let's go back and try to understand something very interesting. Do you remember what is the geometric meaning of LFP and UFP? Now I am in the Riemann Darboux sum, not Riemann Darboux Stieltjes. Okay, this I will call it Riemann lower Riemann Darboux Stieltjes sum. Okay, if you want quite a mouthful, or lower alpha sum, that will be easier to say. Okay, but I am just looking at this. What are the geometric meaning? This is the sum of the areas of rectangles which are inscribed in the region, and this is the sum of rectangle which is which covers the region. You understand that? So this is for any partition P. Is that correct? So now think carefully. Now P and Q are any two partitions, arbitrary. Okay, not necessarily Q refines P or P refines Q, right? And U of Q. You understand this? Two arbitrary partitions I take. What do you think the relationship between these two should be? Use your geometry, you should be able to guess it. Yes, because this is sum of areas. Let us look at the picture like this. So this is the area. Okay, these are the areas. Whereas with respect to any other partition, whatever be the partition, this will be the area. Right? So what do you guess? Yeah, that is the lower sum of the function with respect to any partition should be less than or equal to upper sum of the function with respect to any partition. Okay. Remember, P and Q are arbitrary. Okay, the geometry suggests this must happen. So we want to prove that it does happen. Okay, do you understand this? Okay, so we will make it a lemma LF. We will prove it for any increasing function. This is less than or equal to U F Q alpha, where P and Q are arbitrary. Partitions of the interval, etc., etc. How do you prove this? Yeah, very, there's a very easy trick. The trick is, again I will use a notation, but you should understand the notation. What you do is put all the nodes of P and Q together. You understand that? So I get a new partition. Yeah. So call this new partition as pi. See, pi stands for P, P stands for partition. So I can as well write P1. Okay, maybe write it P1. P1 is a partition P union Q. What is the meaning? I just now explained. What is that? Take all the nodes of P, take all the nodes of Q, and then put them in the natural order. There may be some overlap also. For example, in the earlier case, okay, my thing might have even had 1 by 2 here or 3 by 4 here, right? So what do? I put all the nodes, and if the nodes is repeated, don't worry, but put them in order. You understand that? That's why we write it as a union. When I write a set theoretic union, repeated elements are identified only once. You understand that, right? Okay. Now, what is the relation between P and P1, Q and P1? Yes, P1 is finer than P and finer than Q also. Now that's a trick. That's a trick. Now let us look at what is the relation between LF P alpha and LF P1 alpha. Because P1 is finer than P, we know that lower sums increase. Therefore, this is equal to that. Now, keep P1 fixed. Now, what is the relation between U of P1 and alpha? This is P1. Right? We know with respect to the same partition, lower sum is less than or equal to upper sum. Now, what is the relation between U of P1 alpha and U of Q alpha? Remember, P1 is refinement or finer than Q, right? Therefore, what do we know? Finer the partition, the upper sums come down, right? Therefore, this is less than or equal to U of Q alpha. Do you understand this? Do you understand why it happens? Yes. Do you understand why this happens? This always happens, we know. So what is it that we have got? L of P alpha is less than or equal to U of Q alpha. What are Q and P? Any two arbitrary partitions. Was that obvious? Yes. If I take alpha to be the standard alpha x equal to x, for that function, geometry told us this must happen. Okay, we proved it. Do you like this? Right? See, you see that how geometry makes us even guess the result and also gives a proof. Okay, so pause, review, proceed. Okay, now I think we can say what we want. So we make a definition now. So remember, what was our reason why we introduce upper and lower sums? We introduce upper and lower sums as some kind of approximation from inside and from outside of the graph, right? The region enclosed by the curves, we know that. Okay, right. Or the area under the graph is what they usually say that. Okay, very good. Now we want to find the area. How do I do that? See, there is some kind of inherent urge in human beings. They always look for a symmetry. What is the kind of symmetry I want here? Is look at the region, okay, something like this. Okay, I want to exhaust it by means of from here, okay, from inside, and I also want to approximate it from above. Are you following? Yeah, that is, I want to approximate the area under the graph both from inside as well as from outside. Okay, that is the kind of symmetry I want, right? And what have you seen now? When I take finer and finer partition, the lower sums gives better approximation to the area, right, by increasing, and upper sums give a better approximation to the area by decreasing. All right? Okay. So what is a very natural thing, if at all you want? I want to say I know the area. That means the area I can approximate from both from inside and from outside. So what is the obvious definition I can make? Look at the LUB of LFP alpha as P is any partition. Okay. Now why should this exist? This is a set of numbers, right? Why this set of numbers? I won't talk about LEB. I want to say this set of numbers is bounded above. But we know each of these numbers is less than or equal to m into alpha b minus alpha a. Each of these numbers, right? Therefore this set is bounded above and is non-empty. Therefore the LUB exists. It's non-empty is okay, clear, right? P take P to the partition A and B alone, you got it. Okay, right. Are you following? Okay. So this is non-empty subset bounded above by this, therefore LUB exists. Okay, that means essentially you try to exhaust from inside. Okay, you got something. That thing we will call it L of F alpha. Okay. Sometimes I will come to that. Textbooks also write like this: A, B, F, D alpha. They call A lower B, therefore call it lower integral. So what does this stand for? This stands for if I am allowed to approximate the area from below, from inside rectangles. Okay, what would be the maximum possible area I can get? That's what LUB. Maximum possible meaning in mathematics. In analysis, it's LUB. Okay, right. So I call this a lower integral, but I find this is much easier because writing this takes a lot more time. And if there is some other line in between, this bar, is it A here? The bar is for here. Okay. Suppose there is a complex number, you may think Z bar, right? Okay. So I find this notation, this is what my standard notation, this is easier. Okay. Now if you think you had understood, so I have done 2 lectures now, explained very, very geometrically. Now you should be able to do what do I mean by approximating from above, and what should I call it, and how should I define it. I define lower integral corresponding to lower sums. Remember, for lower sums what did I do? Least upper bound. It's not greatest lower bound. Why should I take least upper bound? Because when I take better and better, finer and finer partitions, I get a better and better approximation. The error between the actual area and the inscribed area is becoming smaller and smaller. So I have to keep on taking better approximation. So I took LUB. You understood? Very good. Now what should be the corresponding thing with respect to upper sums? I'm sure all of you will know that. Okay, and don't be afraid, just make a guess. So I take the set U, F, P alpha, where P is any partition of the interval. Right? What did you observe? As I take finer and finer partition, upper sums come down, and therefore the error from upper sum minus the area under the graph becomes smaller and smaller. Therefore what should I take here? I should take the GLB, the minimum of these things, right? So this is the one. If I can take this, yeah, this will be my area, upper sum. But if I take here, I'll get a smaller area. Right, so I keep on approximating. So I should take the GLB. And what should be the notation? It should be UF alpha. Or what should be the standard notation textbook sometimes? And what should I call this? Upper integral with respect to alpha. If alpha is the identity, we will simply say upper integral to the integrator or weight function alpha. Have you understood? Okay, so I have defined for any bounded function and for any increasing function alpha on the interval AB, I define what is meant by lower integral and upper integral. So lower integral in some sense tries to approximate the area under the graph from inside. Upper integral tries to approximate the area from outside. Very good. Now what did I say? The human nature is to look for some aesthetics and symmetry. So when do I want to say I know the area? If both these approximations which I can should be the same. That is, when I try to approximate from inside, I get lower integral, from outside upper integral. I want to say I know the area under the graph if these two integrals are the same. So that's the definition. So definition is, we say that f is alpha integrable, okay, or Riemann Darboux integrable if alpha is identity function, alpha x equal to x. Sometimes alpha integral also called Riemann Stieltjes integral. Stieltjes. Usually one pronounces this is steel. Just is this Stieltjes integral. Okay, I hope you know how to write it in Devanagari. Okay, our government should be proud of me. So this is, we say if what happens, u of alpha equal to L of alpha. That means I had approximated the area from below as well as from above when alpha is the identity function, but using the JM intuition we say this for even alpha integrability. Is that clear to all of you? Sure? Okay. Now I have a very okay, pause, review, proceed. Okay, I have an important question. What is the relation between the lower integral and the upper integral? You remember, we know the relation between upper sum and lower sum with respect to distinct partitions also. Now what I am asking is, I define this, what is the relation? What is your guess? First make a guess, then we will prove analytically. Yes, because you are this is the maximum possible area from inside, this is the maximum possible area from outside is coming down. Therefore I should expect this. Are you following this? When alpha is identity, of course. Now the proof is easy. Okay, so how did this is what this is the LUB of what? This is LUB of LF P alpha. Okay, P varying over this, and this is GLB. It will be a good idea not to write P but some other partition. Okay, for Q is again arbitrary partition. Okay, right, this number is this. Now I want to know how to compare. What I know is each of these numbers LFP alpha, right, this number is less than or equal to this number, whatever P and Q are. That's what we proved. Okay, we want to make use of that. Yeah, right. So what I know is this is more generally for LUB GLB. Again, in my upper bounds lower bounds I might have done it in the video, but I will go through this in this quick context. Fix one Q. Let us look at U F Q alpha. Right, for every P here, that is every number here, LFP alpha, we know that LFP alpha is less than or equal to this for every P. So therefore what does it mean? This is an upper bound. For which set? For this set, as P varies. You understand? Therefore this is an upper bound. Therefore the LF alpha, this is a LUB of this set of numbers should be less than or equal to UF Q alpha. You understand this? For which Q? This is true for every Q, right? Now reverse the roles. Now as Q varies, this is the set, we are capturing this set of real numbers. So what did we find? this is a fixed real number. This real number is less than or equal to each of the numbers here. So what does that say? This says this is a lower bound. For which set? For this set of numbers, right? Therefore, but then what is my UF alpha? That is the greatest lower bound for that set. Therefore, what do I know? This lower bound should be less than or equal to the greatest lower bound. Therefore, I proved it. Okay, please pause, review and proceed. This tells us something interesting. Therefore, if I want to know when f is alpha integrable. This is by definition if and only if uf alpha, LFF alpha equal to uf alpha. But what I know is LF alpha is less than or equal to uf alpha. Therefore, if I want to prove this equality, what should I do? I have to prove LF alpha is greater than or equal to uf alpha, or uf alpha minus LF alpha, right? This is always greater than or equal to 0. If I prove this less than or equal to epsilon for every epsilon positive, then I know these are equal. Have you understood this? Yeah? Sure? Okay. Right. I'm just making small observations instead of jumping into a theorem quickly. Okay. Try to work with this and do not worry about exam writing, etc. You learn this. After that, you read your class notes or textbook, okay, and prepare for your exams. You will score high, but your understanding will remain with you. That's more important. Okay. Is it all right? Okay, let us look at it. Now let's look at another thing. Suppose I have a sequence of partitions Pn. Okay. So that LFPn and UFPn both converge to the same number, let us say capital A. You understand this? Right? Then I want to know whether f will be integrable. Look at in the first day lecture and second day lecture, our examples, I constructed a sequence of partitions depending upon the function or whatever the data available to me. Then we found out something interesting. Please go through that. This is how you discover mathematics, you enjoy mathematics, not by just routine line by line checking. That only show that you know how to check logically. Okay, but you want to be a creator, you want to discover mathematics on your own. Okay, will it be integrable? Yeah, right. Now let us look at that. What will be the relation between LFPn or Pn alpha also, if you want? Okay, LFPn alpha and LF alpha, this will be less than equal to, right? And this is less than equal to UF alpha, this we know, but this is less than equal to UF Pn alpha. Do you understand this? Yes, right. Now I'm sure all of you know what I want to use. Yes, use sandwich lemma. Where does this go to? This goes to A and this goes to A. Therefore it forces this goes to A and this goes to A. Therefore f will be integrable. Do you understand? Do you enjoy this? Yeah. Now let us look at that. Do I have to give examples of integrable functions? We had already done many examples. Alright, don't worry, we will again go slowly, but before that let us do one more thing. Okay, right. Let us look at what should I do now? No, let us prove Riemann's theorem. With that we will stop today and we will use it in the next lecture. I have, I think, about 32 minutes, so I should be able to prove this. So f etc, alpha etc, standard. Okay, I'm not going to explain all those notions. Okay, then what I want to say, I want to say f is alpha integrable. Okay, if and only if for every epsilon positive there is a partition P, okay, so that u f p alpha minus L f p alpha is less than epsilon. We already observed one thing. What did we observe? You see that? Anyway, we'll let us go slow. Let me assume for the time being alpha equal to the identity function. That, okay, alpha, that is I am dealing with only Riemann Darboux integral. How to change for alpha will, okay, it will be a good exercise for you. I will of course explain how to do it, don't worry. Okay, now suppose f is integrable. Okay, suppose f is alpha integrable. Let me just do with the general case, alpha increasing function integrable. Okay, I want to say, and let epsilon be given, right? Then what do I know? Then if since f is alpha integrable, I know L f alpha equal to u f alpha, right? Okay, but what is L f alpha? It is the least upper bound of a set of real numbers. And if you are given epsilon, if you had gone through my lectures on LUB, GLB, you should know what to do. The only way to exploit least upper bound is least upper bound minus anything, any positive number. Therefore, let's look at LF alpha minus epsilon. This is the least upper bound of certain numbers. Therefore, this is not an upper bound for the set. Which set? LF p alpha. P. For this set, this is not an upper bound. So, right? If it's not an upper bound, what does it mean? This is less than some number LF p alpha. You understood this? Okay, there exists an element of the set which is strictly greater than this, and the same thing applied to UF alpha now. UF alpha is the GLB of some set. So how to exploit the GLB? GLB is the greatest lower bound. Okay, therefore anything greater than that will not be a lower bound. Therefore this is not a lower bound for which set? For the set UF p alpha. UQ alpha, let me write Q. Okay, so what does that mean? This is not a lower bound. Okay, that means there is a thing so that UFQ alpha will be less than UF alpha epsilon. This is not a lower bound, therefore there is an element which is less than that. You understood this? Okay, what am I supposed to prove? Keep that in mind. I want to say there exists a partition P so that UFP alpha minus LFP alpha is less than epsilon. Okay, so I have to find a partition. Now for this epsilon, for the lower sum I got a partition P, for upper sum I got a partition Q. Okay, it may be a good idea to have a picture so that you know. So where is that? Where are the things now? It's integrable. Therefore this fellow is UF alpha, which is also equal to LF alpha, right? UF alpha plus epsilon is here, and UF alpha minus epsilon will be here, which is same as LF alpha minus epsilon, because UF, you understand, because F is integrable, LF alpha is UF alpha, right? Now what did I conclude? That LF alpha minus epsilon, which is same as saying UF alpha minus epsilon, okay, that is less than LFP alpha. Therefore where will I mark it? I have to mark it somewhere here. Okay, LFP alpha. And what do I know about U? Here I know that u f q alpha is less than u f alpha plus epsilon. Therefore, it has to be marked to the right of this. But then remember, what do I know? It should be greater than LFP alpha for any P. You understand? You should wonder why I could not draw this picture here. Why can't I draw here? That's because LFP alpha will be less than or equal to LF alpha. Therefore, I can only draw here. You understand that? And similarly, UF Q alpha will be less than this, but it has to be here. Therefore, it has to be somewhere here. You understood? Is the picture okay? Okay. If you want, you can write it. Okay. Okay. What do I know? I know that U F alpha equal to L of alpha. Okay. Minus epsilon. Okay. It is less than L of P alpha. But for any, this is less than. This is less than or equal to U F Q alpha for any two partition upper, but this is less than U F alpha plus epsilon. This is all I wrote, but picture makes somewhat easier for me to understand. Now let P1 be a P union Q, then P1 is a refinement of P as well as Q, right? Therefore, what will happen to, let me use a different color scheme. So what are the things? Okay, I will use this here. Okay, this one. So where LF, oh, this is, I don't want that. Where will LF P1 alpha lie? So LF P1 alpha, this is a refinement of P, it should be somewhere here. This is LF P1 alpha, right? And for the same P1, let us look at U of P1 alpha. That's a refinement of Q, therefore it should be somewhere here. You understand that? This will be U of P1 alpha. This is P1. Have you got it? Yeah, so you can write it again if you want. You can write this inequality. So U of alpha minus epsilon is less than L of P alpha, that's less than or equal to L of P1 alpha, that's less than or equal to U of P1 alpha, but that's less than or equal to U of 1 Q alpha, but that's less than or equal to this. You understood that? Okay, now let's look at the picture. Therefore, what is the U of P1 alpha minus L of P1 alpha? They all lie in an interval whose length is at most 2 epsilon. You understand that? Therefore, this is less than 2 epsilon. Have you understood? So, if you wanted, I could have taken epsilon by 2 somewhere above. Have you understood? If you don't like this geometry, you can again use that. U of P alpha is, okay, is U of P1 alpha is less than or equal to U of alpha plus epsilon, and L of P alpha is greater than this, therefore minus of that will be less than minus of this, therefore minus U of alpha minus of minus epsilon is plus epsilon. Okay, this is a very boring way of doing mathematics, but look at the geometry, it very quickly told us. So what have we shown now? We have shown that if f is alpha integrable, then given any partition, say given any epsilon positive, I can find a partition P so that upper sum with respect to that partition minus the lower sum with respect to that partition will be less than the pre-assigned epsilon. Oh, are you happy? Good. Now what is that I have to prove? I have to prove the converse. Okay, with that we will stop. So converse. Okay, so what is that I have to prove? I have to prove, okay, for every epsilon there is a partition P so that U of P alpha minus L of P alpha is less than epsilon. I want to know whether it implies U of alpha equal to L of alpha. Yeah. This perhaps I should leave as an exercise, but let us do it. Okay, right. So what do I know? So given epsilon, there is a partition P. Very good. So what does this say? This says that U f P alpha is less than L f P alpha plus epsilon. Right? Okay. So what do I do next? So I have U f P alpha is less than L f P alpha minus epsilon. Okay. So let us look at the picture. What I heard now? For every epsilon this happens, right? Okay, good. Now what is that I want to prove? Remember, we already know U of P alpha is greater than or equal to L of P alpha. U of alpha is greater than or equal to L of alpha, right? So let us, I want to show something else. So let us look at that. This is my L f P alpha, right? And that is less than or equal to L f alpha, but less than or equal to U f alpha, but that's less than or equal to L f P alpha plus epsilon. You understand that? Given any epsilon positive, there exists a P so that this happens. Therefore, what is the distance between L of alpha and U of alpha? At most epsilon. You follow that? Yes or no? Therefore, this shows that U of alpha minus L of alpha is less than or equal to epsilon. Again, if you want, you can write inequality. U of alpha is less than or equal to L of alpha, L of P alpha plus epsilon, and L of alpha is greater than that. Therefore, negative of that will be less than negative of this. Therefore, L of P alpha cancels. You get epsilon. You understand that, right? And this is already greater than or equal to 0, as we observed. Therefore, we have proved U of alpha equal to L of alpha. That means F is alpha integrable. Okay, this is known as I had given the name. Yeah, this theorem is known as Riemann's theorem. Or criterion for integrability. This is a very powerful theorem. See, what is the advantage of this? Let us look at the earlier case. When I want to say F is, this is something similar to your sequences. If you want to prove a sequence is convergent, what do you have to do? You have to find a real number and show the sequence converges to the given real number, called the limit. Okay, but sometimes I just want to know that it's convergent. In that case, what is the easier way in real analysis? Prove that it is Cauchy. That is given within the given data. I don't have to search for a number. I just have to say mod xn minus xm is arbitrarily small for Cauchy condition. You understand? This is something very similar. What does it say? I want to show F is alpha integrable. For that, I have to compute all possible upper sums, all possible lower sums, and find their GLB and LUB and show that they are equal. Now that thing is taken care. What all it says is, give me an epsilon. It's enough if we find a partition P so that upper sum minus lower sum with respect to the same partition is less than epsilon. Something like a Cauchy criterion. Okay, this is a very beautiful result. In the next lecture, we will apply this to derive integrability of a large class of functions. I hope all of you enjoyed the lecture. And Riemann's criterion is a very powerful tool, as I explained. Okay, it's something similar to Cauchy criterion. Please go through it again with your friends. And I keep saying, do not worry about exam. Concentrate on my lectures. Try to understand, discuss. After that, you simply ignore my videos. You don't know what to worry about. You read your class notes or you read your whatever prescribed textbook. You will see your understanding level is much higher. And not only that, many times just because you would watch the videos, you can jump ahead and go through the proof in your mind. but some small proofs. What you should try is just go through on your own in your mind, okay, even without a pen and paper. Try to go through it slowly. You will see that even big inequalities you will be able to, and you can even, as just now in today's lecture, you already saw 2 or 3 times you were able to guess what the next result should be, a theorem should be, right? So that is discovering mathematics. That is the real fun in doing mathematics. I hope you all enjoyed.